Hey, I'm Laith Namu. I go to Wayland High School, and this is my video detecting terrain vehicle. Okay, now we're going to prove that the face detection system in our terrain vehicle can run the robot even without our wireless controller. So if here I have the controller, okay, and I turn it off, put it down here, and I look into the camera and it detects my face, then it will move even without a controller at our aid. See, I'm not holding any controller. So now this will show off all our features for this vehicle, and what I'd like to point out is that there are very many applications. What we could do for this example, we could help aid the disabled, more specifically the blind. Instead of a dog, you can now have a robot which does your functions perfectly to what you want to do. So for example, if we had a module instead of this wireless controller that you could speak into your as a GPS, or that you could speak into as a destination, then there could be a GPS attached to that module and it will locate a location, and every time you walk up to a turn or something, it will send that signal from the module. Instead of what we're doing right now it will still do it through the XB, but instead of as this controller, it would now hack into the controller and send the controls to our system, and it will, based on the GPS location, it will turn at which points, and it will perfectly work now. And instead of, a dog which you can't always trust all the time, now you have a robot that will do everything for you specifically, and it will detect barriers, and it will stop when you need it to stop, and it'll only move when it detects your face, so always stay close to you. Alright, now let's try it out. So if I just come up to it right here, it detects my face, it moves. Okay? We have that barrier too though. So if I just keep moving with it, okay? I just keep moving with it. Let it stop a little bit over there. Now I just come on and keep moving, it stops. Okay. Yeah. And that's how our face detection works. Alright, let's get this thing started up. Okay. First, what we have here is an embedded operating system in the BeagleBone, which is being portrayed through this screen. We have set the parameters to make sure that it fits the screen perfectly. So what you see here is the BeagleBone embedded operating system, which is a Linux based. And when I started up, I set the yellow pin to be high. Now, what's going to load up here is the basic Linux operating system through BeagleBone. And you know how Linux is, you have to type root to start, but what I did is I bypassed it with detecting my face and then moving, because it will be it already detected my face. Sorry guys, sorry. But yeah, it's already running, but this is once this is fully loaded, I'll be able to portray the image out back to you guys. Just so you can prove. See, I already saw my face just now as I was explaining it. Alright, so this is how it's going to start out. It's going to detect my face. Alright. Oh, it detected my face again. See? Alright, sorry guys. Okay, so I'm gonna... Oh, shoot. It keeps detecting my face. Alright, so I walk up to it. Detects my face. Okay. Detects the pixels. It moves. Alright. It keeps moving forward as it detects my face. I can see. It keeps... See how it keeps detecting my face through the picture? And see how it keeps detecting my face? Alright. So, we can move here. I'll turn on my wireless control now. I think we've had enough fun with proving the face detection concept, and now to move forward. Oh, that's my bad, guys. Detecting my face again. Alright. So now let's move it back. Let's move over here. Sorry. Now, what we're going to do is prove our infrared detection. So what happens if we're going to a wall? We don't want to crash, right? So as we move into this wall, it stops. I can't go anymore. Look, I'm pressing the button, but I can't move anymore. But if the wall moves away, I can move again. So let's just keep moving here. Let's go. Let's keep moving. Look, I can turn perfectly. Zigbee wireless, right? Look how far my distance is from the controller that I'm at right now. So, some features for this face detecting terrain vehicle are movement, turning, light emitting, infrared detecting, face detecting, and projecting the image onto the screen. Now, let's show the simple overview of these functions. So, what we first have is, obviously everything starts with a battery. You know, we have an 11 volt, 4 amp power source that is distributed throughout the entire circuit. Now, this circuit is kind of complex, so I'll walk you through it. So, let's start here first. We have power distributed 11 volts directly into the projector, and then we feed the 11 volts into a voltage regulator, which regulates the voltage down to 5, because you know the BeagleBone, or really any microcontroller, needs no more than 5 volts to operate, or else you might burn it. So that's what we're doing here, so it can run effectively. And then we give the Arduino 11 volts because it's able to resist up to 12 volts. So we give it the full source from the battery, and we power this board up with power, ground, power here and ground here. And I have created a voltage regulator which regulates the voltage through this voltage regulating component, some resistance. This, by the way, is often referred to as a 7805, and some capacitors, so we can create that DC wave that we need. So this also emits 7 volts that we need. So we have three actually sets of H bridges. We have this one here, which will control these set of wheels, which will rotate it this way and this way so we can turn. There are also 2 sets of H bridges here that will control these set of wheels and these set of wheels. Now, may I add, these H bridges are being wirelessly controlled via this Arduino board wireless controller using XBee. Now, what I did here was, basically every time I push down on a button, a voltage goes to an input and sends that input voltage through this transmitting XBee to this receiving XBee, which then decodes the highs and lows from these pins onto these pins, and determining based on if these pins are high or low, determines the direction that the vehicle will move. And we do that through the orientation through the voltage through the H bridge, which I'll get into more detail later. Now, also what we have here is a camera which will detect my face, but that will be powered through this BeagleBone that will compute all my pixels and determine whether or not my face is a face. And also, through the BeagleBone, will project the calculations and the image of my face through this screen. Now that I've explained everything in gist, let's get into it. Okay, so the first thing we need to do is communicate to our terrain vehicle via XBee. So what we have here are buttons, an Arduino board, an XBee, and a power source. Now, by default, we have a resistor pulled to ground. So once we click a button, the voltage will go from the power source to our Arduino board. Now, our Arduino board has a polling code that I wrote that has a case for once there is a high on one of the inputs, it will then tell an output to be high, which is directly wired to an input on the XP, which then transmits a PWM signal to the receiver XP on a corresponding input. Now, once one of these inputs are high, it will then go to another Arduino board that will tell the terrain vehicle to do a specific function. We have two sets of H bridges. Over here are the P MOSFETs and the N MOSFETs. N MOSFETs, P MOSFETs. Now, the way I have that MOSFETs oriented is that once there's a low on this P MOSFET and a high on this N MOSFET, the voltage will travel from here to here. Now, that will also, hence, rotate the motor in this direction. Now, we also, as I said before, this is a 7.4 volt battery. This 7.4 volt battery and the 3 volt microcontroller power that it has here, the difference in that is less than 5 volts, which makes sure that our MOSFETs don't burn out, which is what we want. Now, the two sets of wheels will obviously move in the same direction when going forward and backward, but when it moves in or turns in a certain direction, we need one set to go slower in the same direction than the other set, which will be going at a faster pace, which would allow it to turn, because this is going slower and this is going faster. Now, what we do is, to the other set that we have going slower, we have a PWM of a smaller duty cycle, which means that the pulses of the PWM, or the wave we are transmitting, are farther apart. So when they're farther apart, the average voltage is going to be lower, which means smaller voltage, less speed. So that allows our terrain vehicle to turn in any direction. And that is how we control and move our terrain vehicle. That I myself made the schematics, and through a tool called Express on the computer created a PCB layout and then actually got it shipped to my house. So this is the PCB, or printed circuit board. Obviously this is a rough draft of that. Okay, now I'm going to talk about the infrared emitter part of the circuit. Okay, so the first thing is the power goes to the capacitor and then a resistor to ground. Now, that capacitor and resistor to ground also does a thing known as a high pass filter, but we don't need to talk about that right now. But we should know that that brings down our wave because the DC is being grounded through this resistor. So we'll talk about that later. But what we need to know right now is that this does a 60-degree phase shift every time it goes through a capacitor and then a resistor to ground. So we have 3 of them, which does a 180-degree phase shift. Now, remember how I said that this resistor to ground brings our wave down to actually even below the 0 voltage level? So we actually have right here this resistor and this resistor ground make it that we can add some DC voltage, but not too much, so we divide the voltage. So that's so we can bring it back up the 0 volt line. Now, we have a 180-degree phase shift, and then we need to calculate its frequency. So the way I do that is by using the formula 1 over 2 pi RC. Obviously, R is the resistor and C is the capacitor. Now that we have a 180-degree phase shift, we go to the base of this NPN transistor, which inverts it, which consequently means that it's doing another 180-degree phase shift, which is a total of a 360-degree phase shift now that's looped back, that now oscillates because lapping the original wave over another wave, so it's oscillating now. Now we have let me also point out that there is a resistor and capacitor to ground on the base of this NPN transistor, so that pretty much gives it a return path for the AC wave. And let me also point out that there is an LED on the collector side of this transistor, which pretty much just lets us see if it's working, then the LED would be lit. So we then go to an AC and resistor in parallel, which does the same thing as AC coupling. And then we go to another NPN inverter. This time though, it's no longer AC wave, because this resistor is only 100 ohms and the other resistor on the collector side was 400 ohms. That means that it's going to be amplified 4 times more. That means it will no longer be in the linear range, and now will be a DC line. So that will give us a 50-50 duty cycle to emit through this over here, infrared diode, and then we have to receive the signal. Okay, and now we're going to do the infrared receiver part of the circuit. So when we do this, now we are emitting it through the diode, and now we're receiving it through an infrared transistor. Now the first thing we do is we have it on the emitter side with a resistor to ground. Now that helps dump out any extra energy that's caused from the ambient light, like a DC wave. Okay, now we're going to use back that concept of the high pass filter, which I talked about here. Now that's a thing because the capacitor charges and discharges very fast, and we can let high frequencies, which source with those charges, get by, but the DC can't get by. So we now have a low pass filter, and that's because we're dumping all the high pass or the high frequencies to ground, and we're letting the slower DC get by. Now we have that because our ambient light, some of the energy from that have frequencies that are so high that it's like very fast, and it just rides pretty much a DC line over it. So that lets us dump that stuff to ground. And now we have a capacitor that's continuing through our circuit, but a resistor to ground. That lets now high frequencies, because now not all the light is going to be at such a high frequency, and some of the light is going to be slower, and also it helps tune and create a band pass from our frequency that we emitted. Okay? And now we enter through the third pin, or the negative side of our first amplifier, which is non-inverting, and there is a feedback resistor and input resistor here from the output around to the negative terminal in our amplifier. Now that is a proportional amplification that we'll use to get out from the output, because our receiving wave is not what we first emitted. It's much slower because it came back and it lost a lot of its voltage. So we amplify it now because it's a non-inverting amplifier. The inside's a little different, so it's going to be 1 plus the feedback resistor over the input resistor. Okay, now we send our output around here from what we have a resistor and a capacitor to ground, which is an RC, which helps smoothen out our wave to a smoother line of voltage. It's not exactly straight, it's still a little, like shark teeth. Now we're going to use that line, smoothen line, as a trigger line. Okay, so we are now feeding from our source voltage, putting it through a voltage divider for we have a resistor here, and then after that resistor, a resistor to ground, and then it goes to our negative terminal here. Okay, and so we gave it a specific amount of voltage that we divided from the source voltage to our negative terminal, and we have on our positive side our trigger line voltage. Now all we need is for that trigger line to be over whatever we divided that source voltage to be, for us to take out all of our source voltage from the output, or terminal 7. Okay, may I also state first that terminal 8 and 4 is power and ground respectively. Okay, so now that we have that, may I also say that the resistor, the voltage divider was calculated by voltage input times our second resistor over our first resistor plus our second resistor. Now, this amplifier was a comparator because there was no feedback to the and wired to the output from the negative, so it's a comparator, and that's what allowed us to do this, subtracting and then taking out the source voltage from terminal 7. Now we have over here to the output, we have here the yellow wire that will go back to our microcontroller. Now we need to be within the 3 to 5 volt range, and we were giving it 7.4 volts, so we divided it again using a voltage divider before we go back to the microcontroller, and we also have it hooked up to the buzzer, which you obviously heard throughout the video. So that is how our infrared receiver works, and how our infrared emitter part of the circuit works, and that is our infrared sensor. So I'm going to now show you how I ran the code through the BeagleBone. What I have here is a keyboard and a mouse that I've connected through a port into one USB port into the BeagleBone, and now that's going to be splitting up some current, so I'm going to be running it through the wall to show this for demonstration purposes. So originally my code, I transported through a thumb drive into the USB port, and I put it into a specific folder, and then I changed its location to run it, but I'll get more into that. But for now, let me show you where my original code was and where I had it. So if I go in here, I put it in this folder. Give it some time to load. You know, it's embedded operating system. It's not gonna run that fast. So right here, I'm gonna open it up right here with gedit. Okay, now here's my code that I've opened up. So quick run through this. First, I'm including all the libraries from OpenCV. Then I am, declaring my global variables. And then, if we scroll down a little more over here, we have what we do is setting up the pins. So we're telling which pins to use, and so for example, right now we're telling it to use the yellow pin on startup, and then if it detects our face, we're going to do green pin. So we're both constructing the yellow and green pins here. We're using GPIOs, and then we're gonna go and later down in the code, we're gonna tell it to set this to high when we first start the code, and then when it detects your face, only set the green to high. That's what we'll be doing. So if we go down here more, let me go back up first. So capturing the camera that we plug in, that's what video capture 0 means. And then we're setting the frame variable, and we're setting the size and the width. We set it to be smaller size and width so it can compute faster, or else it would have taken forever to compute our face. So then it's doing all its code here to detect the pixels. If it's in a certain algorithm, then it's your face. And now I have it that if the face is detected, face detected equals true, then first right here, here's the code that I do to set the picture, to create the picture of what it captured from my face, and then I put it to here, so when it detects my face. And here I say for the green pin to be high. This is the GPIO write-up for that. Yeah. And that's basically the run through the code. Alright. So, I also deconstructed at the end, and also, yeah, that's basically the code. So now, if I'm gonna exit through here, so now that we have the code, what we want to do is we want to be able to read that code. So we had to import all the libraries. So what we did was using, it took a lot of work, but we had to decode all the entire code to a bit, and we had to make all the files, and we had to download all the OpenCV libraries into Linux, the operating system, which is Angstrom, by the way, and give it a kernel and drivers and a database tree. We download all of that to make it work, and it had a GCC toolchain compiler that translated the code to binary and installed the drivers. We also did a shell file in the root, and that's basically a script file that orders the things to run, including compiled executable binary files. What we also did now is, you might have noticed this build file here. If we go into open with gedit, what that basically is doing is it's telling our specific code to do to execute all these things. So it's making the executable, and then it's executing the code. Okay? So we now copy this through, I can pull it up for you. So what we basically do is we go to the terminal, and we set it, we cp the file into root. I may already have it actually, one of the command. See, we cp the make LED to the root so that the shell can see it, and it runs the code on startup. And yeah, that's basically the gist on how we got our face detection system work, and how we got our camera to work with it. Okay, so you may remember that I said once it detects my face, it will light the green pin to high. Okay, so what we do is you may have remembered also that we have a logic for where it has an input, it will set an output to a certain value, and it'll run an H-bridge. So what we're doing for running when it detects our face is we take a wire from the green pin, and in order to boost the current, we put in a transistor. But that also means when it's high, we're looking for a low because we're inverting it through that transistor. So now we have this yellow pin connected to that, or actually we have this yellow pin connected to that, and so now our code in the Arduino is saying that once this is a low, it will run this H-bridge to run forward, and that's how we're running our vehicle once it detects our face forward.